Yeah, thank you all. Yeah, thank you, Prakash. Fine. So let me also start sharing my screen, and I will take you from where Prakash left last time. So in this session, I will quickly cover a few concepts through theory, and then I will also take you through a very simple exercise, or a demo, I should say, on IBM Qiskit. And this is primarily for those people who are new to IBM Qiskit. Maybe this could be the first exposure to IBM Qiskit. So I believe my screen is visible to all of you. And let me pull up the presentation. Yeah. Okay. Fine. In the screen, this notification should go somewhere there. Okay. Fine. So today we are typically on session number 4, session number 5. And today we are going to quickly have a review about the Hadamard gate as typically a part of a demo. And then I'll take you through a very simple session on IBM Qiskit, and we will try to see how a few gates can be put to use. And I'll also show you how the Hadamard gate also shows up its what do you call the behavior of superposition. And I will quickly go through a few theoretical aspects about what we mean by algorithmic complexity. And then we will also define the concept of speed up. And we will take a simple quantum algorithm. And the quantum algorithm which we are going to talk about today would be the Josa algorithm. And that would be a small demo which I am going to complete. Right? So that should take about 1 hour and 1 hour 5 minutes. Maybe we are already a little late. So this is a quick review about the Hadamard gate. We know Hadamard gate is a 1-qubit gate, and primarily it takes up the input in the basis vectors ket0, ket1, and rotates this into a superposition of these states and typically puts it into the minus and the plus, or plus and the minus basis vector states. So the Hadamard gate is one of the most commonly used gate in most of the quantum computations and quantum algorithms, wherein we typically take the input from the system, and using the Hadamard gate, we just put this into a superposition of the basis states. So that is one of the reasons why the Hadamard gate is one of the most popular, most commonly used gate out over here. And we know the Hadamard gate has got a matrix representation of 1, 1 and 1 minus 1 with the magnitude of 1 over root 2. We are typically talking about a Hadamard gate which is described over the 2 basis states, ket0 and ket1. When you look at the way this matrix operates, the Hadamard operating on ket0, the Hadamard operating on 1 second, please. There are some people waiting. Yeah. So the Hadamard operating on ket0 takes it down to 1 over root 2 of a combination of ket0 plus ket1. Similarly, Hadamard operating on ket1 takes you down to 1 over root 2 magnitude operating on ket0 minus ket1. So we use the Hadamard gate primarily for converting your typical inputs into a superposition state, and these will be actually presented to the subsequent gates in your quantum circuit. Right? So yeah. So what we will do is we will go through a quick demo of how this IBM Qiskit operates, and then I will show you how this Hadamard gate functions, and then we will move through 1 or 2 other gates as a demo session, and then I'll get on to coming back to the theoretical part to identify what makes up a quantum algorithm, what is the concept of a speed up, and then we will also look at the Deutsch algorithm as well. Right? So we will see a quick implementation of the Deutsch algorithm on IBM Qiskit. So let me show you my screen full, And what I'm going to do is I will typically log into my account. Oh my goodness. Yeah. So this is my IBM Quantum platform wherein I can log in. So I have my account created, and those of you who have not created an account, you can go ahead and create an account. This is free of charge, and you can essentially use the platform to set up your own circuits and test them, either A, on the simulator, or B, you can typically deploy them onto a real environment. Now, IBM offers a free to use bunch of quantum machines, and according to the type of algorithm which you define, you can just select a bunch of these free to offer devices, and then you can typically deploy your application onto that particular device and execute it out there. Right, so both these two features are available. I'm not going to demonstrate the second part as of today. Maybe in the next session I'll just show up a actual example of how you can deploy an application onto the actual device running on the backend. So let me quickly log into my account, and my ID happens to be my email address, and then I will pump in my password. I hope I keep on forgetting the password. See. This should be okay, I think. Yeah. So I just logged into my account. And once I log into my account, I don't know how to pull this off. Maybe I just put it somewhere here. Yeah, I have the platform, and the platform typically shows up my dashboard in terms of what exactly are the jobs which I've fired and how many are pending, what is my queue status, and it will also give me some indication of as to what and where my earlier jobs were running. There is access to a bunch of tutorials, and maybe you can also reach out to these tutorials directly from this dashboard and get onto a quick learning as well. IBM Quantum platform offers you two basic approaches to put up your circuit. One is, we have what is called the IBM Quantum Composer, and the composer allows you to build your circuits using very simple blocks, and every block primarily could be acting as a gate. So you bring in these blocks and then interconnect them and then create your own circuit. So it's basically a drag drop approach to building up a circuit. So that is what a composer essentially does. And the composer automatically also tries to run in the form of some sort of a validation. It tries to run and then shows you and instantaneously the outcome of your circuit as well. So in that context, the IBM Quantum Composer is a very nice low-hanging fruit to set up your quantum circuits. The other way and the other approach is using the IBM Quantum Lab. And using this Quantum Lab, IBM provides you with a notebook, a Jupyter notebook type. But the best part about this notebook is this has got most of the the tools and whatever are the resources that are needed already plugged in. Right, so you don't have to do a lot of pip installs and stuff like that. So most of the things are automatically made available, set up for you. So you get a notebook, a Jupyter notebook, and then you can create your code, obviously using Python. So you can write segments of the code in cells in your Jupyter notebook, and you can run them and then see the outcome of each of the cells execution. So you can run either way. So you use either Python as the core programming language to set up your circuit, execute them, or you can also compose these circuits using a graphical tool. So let me first take you through the IBM Quantum Composer. So I just launched my IBM Quantum Composer, and the moment I do that, it just opens up the complete environment for me. So this is typically the environment that is provided to me through this composer. So what does it contain? if you look at this entire user interface that is provided, the IDE or whatever you call, there would be a home catalog, composer, lab, basically a top level menu. And then you have got a way by which you can browse through all the files which you have composed, your project files which you have composed. And it will just give you a palette of all the instructions, a palette of all the gates which are available. And this is your work area. The one where my mouse is currently hovering over, that is a work area where you actually create your quantum circuit. Now, when you create your quantum circuit, unlike maybe your normal digital logic circuits, you use the gates, but you really do not talk about setting up the actual interconnect wiring and stuff, things like that. So here, what you essentially try to specify is identify what will be the quantum level inputs, and you identify what type of gates process these inputs in stages as the computations move from left to the right. So the left to the right is something analogous to a time axis. Okay, and then you place the gates, and gates will identify the computation that typically gets carried over from the left side to the right side as the computation is triggered. Right. So this is, if you look at this, this one line is typically meant for, let's say, one quantum input, maybe a quantum line. We call this as the Q0 line, and the Q1 line indicating the fact that you are trying to formulate a circuit using 2 quantum bits as an input. And you also have an associated set of classical bits. And what are these classical bits? The classical bits are those bits where you typically capture the outcomes, measured values from a quantum circuit, and these classical bits will show up the actual states, right? Remember, after measurement, the circuits will collapse. So post the collapse operation, the data typically is captured into the quantum lines. Okay, so sorry, the classical bit lines. Fine. So this is where anyway you compose your circuit, number 1. Number 2, and onto the right hand side, what happens is, as you drag and drop and create your circuit, right, this quantum composer automatically creates an assembly implementation. We call this as a quantum assembly implementation. This is basically a register level representation of these particular gates and the associated programs. So that entire program gets created. So this is your QASM, the quantum assembly implementation of your circuit. Depending upon how you drag and drop your circuit elements, the instructions get added out over here, and this forms the basic circuit. So which also means the fact that this circuit is good enough. If at all I store this, I can probably recreate my graphical representation of my circuit as well. So this is the QASM representation of your circuit. And right below, you have some outputs which are generated. One is in the form of a state of the entire system called as a state vector representation. Then you also have got another representation which is typically typical to, let's say, the IBM Q representation. We call this as a Q representation. Right? 1 second. There is some message which is probably coming up on the chat. Yeah, I can't see. Okay, maybe those have been notifications about people who have been waiting there. Good. So this Q sphere essentially is quite similar to a Bloch sphere, but it's not a Bloch sphere, though. The comprehensive combined state of the system is what is shown on a 3-dimensional cube. And by default, the cube is identified to be positioned in such a manner that let's say north-south axis is one axis for representation, the east-west axis is the second axis, and basically the in and out axis is the third axis. And then, you know, the entire sphere is split up into several regions and segments depending upon the number of states you wanted to display. So here, if at all I have a 2 qubit, then I will typically have 4 states, and the states will be 0, 0, 0, 1, 1, 0, 1, 1, and those 0, 0, 0, 1, 1, 0, 1, 1 will typically occupy the top corner here, the north and the south, east and the west areas of my Q sphere. So we will see more complex representations of the Q sphere. So this is a consolidated representation of the entire system. Okay. This left-hand side graph is very important because it is also going to denote the overall probabilities of your entire system. So currently, it typically tells me the fact that the system is said to be in state 0, 0, and the probability of my observation is about 100% because it is already a measured output. Okay. So this is how your composer essentially works. So what I will do is very quickly, I will just create a new project. And when I create a new project, the system creates to me with the hope that I might be probably setting up a 4-qubit circuit. So that's the reason why it gives me a qubit registers of size 4 and a corresponding classical registers of size 4. And these qubit registers and the classical registers are called as the Q register and the classical register. These are basically registers which hold the quantum state for the Q registers and the classical state for the C registers. And right now, let us say I don't want about 4 bits each, so I can just reduce that down from 4 down to 2. So this is the minimalistic circuit. And at this particular point of time, notice my system is said to be in a specific state. So what is that state? Whenever I create any input out over here, by default, IBM Q or the IBM quantum environment will set these inputs to ket 0. So this is ket 0, and similarly this is also ket 0. So together my state is in state 0, 0. And that state 0, 0 is what is actually depicted out over here without any input. So that is my default. And similarly, you can see this is your state 0, 0 out over here, showing up with a probability of equal to 0. Okay. What I can now do is I can probably bring in some elements and then create a small circuit, right? So let me just quickly bring in some elements, right? So I can just say this is my knot, right? So the moment I bring in a knot out over here, obviously I'm now complementing Q0, and the moment I complement Q0 out over here, this state now becomes 1, and this state is now equal to 0, the same state. Now, once again, it is also important to understand the fact that Q1 is the most significant bit. Q0 happens to be the least significant bit across this 2-bit quantum data. So remember, so this always will be the least significant bit. As you keep on adding more and more quantum bits, they will tend to be on the most significant side. So here, now I can now say the fact that Q1 will be equal to 0. Q0 is equal to 1 simply because this is the representation for a knot, right? So obviously now notice the fact that my state is now equal to 0, 1. This is 0 and this is 1. Fine. And accordingly, you can also see the fact that on the Q sphere, the state is now denoted to be equal to 0, 1. Same is with respect to the state vector. Okay. So I can typically also do some other operations as well. So if at all I take this, drag it down out over here, obviously now I'm complementing Q1. So because of which the state now will be equal to 1, 0. So I'm complementing this. If I drag in another element, put it out over here, both the inputs are now complemented, and now the resultant state will be equal to 1 and a 1. So this is how you can just typically drag drop and then create some very, very simple circuits. So what I will do is I can just select one of these, remove that. Maybe I'll select this, also remove that, and then come back to the initial state. Let us see how my Hadamard gate essentially works. So this is my Hadamard gate. So I can drag in and then dump a Hadamard gate somewhere out over here. Okay, and the moment I have done that, just see what has happened. The Hadamard gate will take this Q0 input and then puts it into a superposition, and that particular superposition is essentially an equal probability of either a 0 or a 1. So because of which the state of the system will be most significant bit is 0. The least significant bit could be either a 0 or a 1. So you have got a combined set of these two states, 0, 0 and 0, 1. And if you just hover your mouse here, you will see the fact that it is the state 0, 0 with a probability of 50% and state 0, 1 with a probability of 50%, right? Similarly, if you just take this and then bring it down out over here, you are adding now two Hadamard gates. We call this as H2 operation, and this will now bring in the entire system out over here. This will be either in superposition of 0, 1. Similarly, it will be in a superposition of 0, 1. So you have got now all the 4 possibilities of possible states and that also now gives you the probabilities, and the probabilities would be equal 0.25 probability. So it's about 25% probability for state 0, 0, 0, 1, 1, 0, and 1, 1. So Hadamard gate is one of the very common and popular type of a gate that is used to put an input into a superposition. So what, once again, for demonstration purposes, I will remove this. I'm going to use this Hadamard gate. Remember, this Hadamard gate is operating on ket 0. So if at all I bring in this out over here, I'm now having the Hadamard gate operate over ket 1. And if at all I operate over ket 1, see what has happened here. Once again, I'll have the states out over here with the same probability. But because of this Hadamard gate, the Hadamard gate operating on ket 1 will be equal to 1 over root 2 into ket 0 minus ket 1. Remember, that minus basically is implemented as a phase shift. And that particular phase shift is denoted out over here by this red color. And it tells you the fact that the phase angle is phi, whereas here the phase angle is 0. Right? So you can also see that phase state that is represented out over here as well. Fine. So that is how your Hadamard gate works on an input which is equal to 1. How did I get a 1? The 0, which is the default input, I have complemented it using the NOT gate. Okay. We have also seen, let me remove that for a minute. I'll remove this also for a minute. We have also seen a conditional NOT gate. So let me show you how the conditional NOT gate also works. So this is the representation for a conditional NOT gate. Okay, I'll bring it here, connect it across. So this is now my conditional NOT gate. And the conditional NOT gate typically does the following. It examines the condition on this Q0 line. And if it is equal to 1, it will trigger this particular NOT gate to operate. So right now, the input out over here is a 0, because of which this is not triggered. So the NOT gate will not complement Q1. So the outcome will be once again a 0 and a 0. Whereas the moment I bring in inverter here, that will now complement Q0. So Q0 now becomes 1. So this control line now becomes equal to 1, and that will cause the target line Q1 to be complemented. So now you will have the state to be equal to 1 and a 1 here. So this one, the input, and this one is the complemented second input out over here. Okay, so this is how your conditional NOT gate also works. So let me remove that and this as well. Let me show you how the swap gate works. I'm not sure whether the swap gate was introduced or not, but let me tell you how the swap gate works. So this is a representation for a swap gate. The swap gate does the following. It is primarily a 2-input gate, and it takes the 2 inputs and then, typically swaps the quantum states of both these 2 inputs. So what we will do is, initially it was 0, 0, and then the moment I use the let's say the swap here, it is swap both the inputs. So once again, the output you get is nothing but 0, 0 only. So no major change is what is seen. So what I will do is I just add this in a moment. First, let me bring in an inverter here, a NOT gate here. So now my system is in a state 0, 1. Right? So this is 0, Q1 is 0, Q0 is equal to 1. So that is the state which I observe. And now what I will do is I will now bring in this particular swap gate here. And the moment I bring in the swap here, now see what will happen. Right? The outputs are generated in such a manner that the quantum states are typically flipped across. So this is a complemented state. So from 0, 1, I now get a 1, 0. Similarly, if the inputs were 1, 1, you would not really see any change, because after swapping also, the input will be a 1, 0. So I can also do the following. If I just bring it out over here, then what will happen? Initially, it was a 1, 0. 1, 0 now becomes a 0, 1 because of this swapping. So this is the way the swap gate typically works. It swaps the input quantum states. Okay, so I'll remove this. Yeah, give me a moment. Yeah. And what I will do is I'll show you once again very quickly another small gate for you, which is the Toffoli gate. Now remember, the Toffoli gate is something also called as a CC NOT gate, a very, very popular gate. You require 2 control lines, and one target line. If both the control lines are 1, then only the target line fires and it will complement the target input. So for this, you really require 3 quantum states. So what I will do is I will just go across here and then convert this into a 3 quantum gate system. So you will now see this is Q0, Q1 and Q2. Okay. So I can probably bring in an input here. Okay, so that input will now make the system to be equal to 0, 0 and a 1. So that is a state you observe out over here as well. I will now bring in a CC0 gate, put it out over here. And now what is happening? Will this gate fire? The answer is a big no, simply because this input is a 1, whereas this input is still a 0. So across these control lines, one of them is a 1, the other one is a 0, because of which this guy does not fire. So to make this fire, see, notice the fact that Q2 initially is equal to 0. So the state of the system is 0, 0 and a 1. So this is the current state. Whereas if at all I bring in another input here, so the state of the system will be 0, 1 and a 1 without the Toffoli gate. So let me first remove this one more time. I'll bring in these 2 control inputs to be equal to 1 and a 1. And notice the fact that my system is now put into state 0, 1, 1, 0 here, 1 and a 1. So that is the observed state. And now if I bring in this Toffoli gate, this gate will fire. Why does it fire? Both the control inputs are 1. Because of it is being 1, Q2 will be now complemented. And when Q2 is complemented, the outcome now will be equal to 1 for Q2. So the system state will now be equal to 1, 1 and a 1. So just see that it just switches over to the state 1, 1 and 1. And if I just remove any of these, once again, the CC0 gate does not fire. It leaves the inputs unchanged. Right. So this is how you can typically look at different type of gates. You can bring them in out over here and then connect them and then create your circuit. Right. So let me also show you one small example here. So I will go back to my system, which is a 2 quantum gate system. Okay. I am now going to have my system input is equal to 1 and Q1 is at 0 state, and I can now put up a Hadamard gate here. And the moment I put a Hadamard gate, what do you expect? You get typically this input to be rotated and the system will come down to a superposition state. And in a superposition state, now you see the fact that the probability of both of them is equal to 50-50. Secondly, notice the fact that this Hadamard gate is operating over a Ket1 as an input. Because it is a Ket1, you see the fact that there is a phase angle of phi. My goodness, what has happened? Give me a moment. Yeah. Okay, so it just gives you a phase angle of phi out there. Now, what I will typically now try to do is like this. Remember, this Hadamard gate has put the outcome in superposition. So you just see the fact that this is in a superposition and the state will be either 0, 0 or 0, 1 with an equal probability. And the moment I bring in this measure, so this is the way to measure, you will now notice the fact that the system will start collapsing. It just collapses down. Okay. Okay, so what has happened? The system collapses down to input which is 0, 1. And if you just notice the fact that this is now state 0, 0 with a probability 48.53 and this is a state 0, 1 with a probability of 51.4684. The probabilities are now once again not 50-50. Hadamard gate is supposed to be giving you equal probability of 50-50, but there are noise which is there in as part of your system, and all other simulation related aspects will play their own role, and you might not be exactly getting the equally distributed probability. But notice the fact that the moment I add up this measurement, system state will collapse, right? Collapse to one of the so-called stable states, either a 0, 0 or a 0, 1. So please understand the importance of measurement as well. Okay. So with this, let us just hold on for some time, and then we will get back to a small discussion about the topic for today, and then I'll come back to this session, our demonstration on IBM Qiskit. So any questions if you have got so far? I can probably answer them. Yes, sir, you can ask questions. Yeah, people, you can just ask questions in the chat window, and I will answer them as soon as I see that pop up here, or maybe towards the end of the session. Okay, so once again, coming back, right? So we just had a quick demonstration of IBM Qiskit through IBM Quantum, right? So as I told you, IBM Quantum provides you a dashboard interface, and then you can create your jobs. Now, these jobs are essentially nothing but the execution of your quantum circuits, and you submit these quantum circuits for actual execution, either on a simulator, or you can put them up onto the real device. Now, there are a variety of devices which are available and hosted. Some of the devices with a higher capacity are normally available for a paid account. And IBM also has made available some low-end devices, I should say, maybe devices which about 11 gates and 17 gates and 15 gates and stuff like that. And these devices are made available at various centers, right? So I can now look at which exactly are the platforms that are available for running my quantum circuit, and then I can typically submit my job onto that particular machine out there, onto the target device. Now, the moment I submit my job gets queued depending upon, once again, the traffic load or the queue or size that is there currently. It might probably take a few minutes for the circuit to be set up and executed, or it might take maybe a few hours as well. I was not very fortunate all the time. Whenever I submit, especially from India, it typically takes somewhere around 18 to 20 hours for my job to get scheduled and executed on the target device. Right. So as I told you, it also comes with a simulator. That simulator is called the AIR simulator, AER simulator. And the simulator will give me an opportunity to execute my circuit. Definitely not on the physical device, but it will also allow me to execute my circuit. And for simulation, I can also specify the number of simulation runs I wish to execute. So these are called as shots. I can specify, okay, I would like to run my code on the simulator for about 1000 shots. And at the end of these 1000 shots, I just collect all the outcomes and then probably see the overall performance. Okay, so as I told you earlier on, you have got essentially two ways or an approach to set up your system. So one way is you can just use this entire IBM Qiskit along with the infrastructure, directly set it up onto your local machine. For that, you can download Anaconda, install Anaconda, and Anaconda automatically provides you with a Jupyter notebook. And you can essentially pip install whatever are the packages that are needed or modules that are needed for IBM Qiskit, number one. Or you can also use Google's Colab, right? If at all you don't want to set up anything onto your machine, you can also use Google Colab notebook, and that Google Colab notebook comes up as a standard infrastructure for developing Python applications. There also you can now pip install and then set up your environment. The third way is you can also use any other standard Python installation with a suitable IDE. It could be Spider, PyCharm, Ideal, or whatever. And you can also pip install the required packages, right? As we all know, Python 3.7 or higher is what is preferred. And this obviously works on most of the standard operating systems which we are aware of, like Linux and Windows and Mac OS and things like that. Okay, so what are the packages you need to install? You just say pip install Qiskit, and you can also say pip install Qiskit IBM runtime. Okay, so this is what is essentially needed to be set up. Okay, once you have done that, you can just open up any of your idle or any other editor, create your application code, and you can run it on your Python based environment, or you can also typically put this entire application onto what we call as the notebook that is available on IBM Q. Remember, I told you IBM Q also provides you with a notebook. I'll show you also that sort of a notebook and how the code looks like in a moment. Having done that, you have got once again two options. You can run the entire code on a simulator, or you can also run it to execute on the quantum device. And you submit your job and it runs on the quantum device. Obviously, it carries out a lot of other operations. It takes your code, converts it into appropriate code that is good and ready for loading it onto the device. This is called as transpilation. And having done that, it will more sort of optimize also the code, and finally sets it up onto the device, and the outcome that is generated as the result of your execution is sent back to you onto your system. Okay. Whenever I want to use this quantum device, I have to use the API token. Now, the API token is a unique key using which you authenticate yourself and then gain access to the far-end quantum device. And that API token is available whenever you set up your account. So when you set up your account, kindly grab this API token and then save it onto your machine. That's about the process and the procedures. Fine. So let me see. There is a query that has come up. Yeah. Fine. Okay, so Prakash has added some additional information. So you can see that there are a lot of resources which are available, free, offered by IBM, taking up anywhere from 5 up to 30 qubits. You can just even try these sort of quantum circuits free of cost. Thank you, Prakash, for the input. Let us very quickly talk about classical algorithms. We will typically understand what we mean by classical algorithms. We will also identify what we mean by the concept of speed up, right? Everyone knows about classical algorithms and the importance and significance of data structures, right? Data structures play a very, very important role in ensuring the fact that your algorithms happen to execute efficiently. Rather than having your data in an unstructured form without the help of a structured way of putting up your data, you might lose out on effective means to retrieve the data, to access the data, to traverse over the data, to search for the data, and so on and so forth. So normally we build data structures which ensure the fact that your algorithms become efficient, right? A classic example is a search. Let us say I have a list of values which are put up, let's say, in an array, and these are typically not ordered at all. So randomly, as I get the data values, I have placed them into this array. And if at all I have to search for an element, I have maybe a brute force technique wherein I loop over, iterate over this entire list, searching for every element starting from the first occurrence and probably running down to the last occurrence. And if I can't find an element, I have made n tries, and after n tries, I can declare the fact that my search is unsuccessful. And if I'm lucky, the very first instance itself, the search element could be picked up from the array. Or if I'm not so very lucky, it could be the last probe, last search, which I performed on this array to retrieve the element to be searched, right? So which means what? On an average, the best case is one search probe, the worst case is n search probes, and on an average we say that I require n over 2 search probes. Remember, if the same data, if it is sorted, then I can probably apply a binary search logic, and this binary search logic does the following. With every probe, you are now going to reduce the size of the search, the range of the search, by 1/2. right? Because of which you can always say the fact that if at all you have got a list of 1000 elements, all you require is a maximum of 10 probes. So 10 searches is what you essentially require so as to determine the exact position of the element. So which also means the fact that putting up your data in an appropriate structure always gives you that sort of an additional advantage, right? So now when we talk about algorithms which perform some sort of either a computation or a search or an update or a retrieval, whatever, we identify how much time this algorithm is essentially taking. Now, we don't really measure the actual time, but we measure the number of operations that I need to carry out in the context of the size of the data. Right? So this is also called as an order of n, where n is the size of the data. So if at all there are n elements, and if my algorithm takes a time which is in direct proportional to the n, the value of n, then I say that yes, I have got an algorithm which is of order n. Right? There could be some algorithms irrespective of the size of the data. Maybe I will require constant number of operations to be performed. Then I say my order of complexity is a constant value. A classic example is something like a hash search. Or I could have a scenario wherein I say I have an algorithm, and this algorithm is typically an algorithm, more specifically like the traveling salesman algorithm and stuff like that. There the order of complexity is of the order of 2 raised to the power of n, sometimes n square, etc., etc. These are primarily we call them as exponentially increasing type of complexities, non-linear in nature. So these non-linear complexity algorithms are very, very problematic in the sense that the moment I just add up even one single element, the number of operations immediately doubles. So that is a dangerous approach, right? So what I need to do is come up with some algorithms which always take maybe a time which is of the order of, let's say, a square root of n, a cube root of n, log of n, stuff like that. So the moment I get those sort of algorithms, obviously I am having an approach wherein I can handle extremely large volumes of data. I can perform these operations on very large volumes of data, yet I am assured that I'm going to get the result in deterministic time, right? So this is where our quantum algorithms essentially come into picture. Okay, so let me take you to that. This is a small example of what we mean by speed up and algorithmic complexity. Let me not show that here. So when you look at the quantum functions or quantum operations, we can look upon this as if it is a black box which takes some input, performs the so-called operation, the function or the computation, and generates an output. Right? So this is a very simple model. And how do I identify this model? This model can be also identified as an input, which is a series of zeros and ones. So there is an input string coming out from the alphabet 0, 1, and the string could be of size n. So there are n bit input. I do some computation and generate an output. Output once again is defined over the same alphabet 0, 1, and the output would be once again a string of zeros and ones of size m. And in that particular case, I now define this computation as a functional relationship, like f is a function defined over sigma n deriving down to sigma m, where n and m are positive integer values. So with this model, what do we mean by the input? The input that is given to this computation box is called as a query. And what is that query? Query would be one input string out of all possible combinations of the input strings. So I will say that the input string x is a subset of, or probably belongs to, this sigma n, a collection of all strings over 0, 1 of size n. And this is the one which triggers the computation and generates an output. And the output once again is said to be belongs to sigma m. So it is a computed result. Okay, so here is a small example to illustrate this concept. If at all I talk about an OR function, right? OR function is defined, let's say it is a 6-bit OR. So I just said it is a function operating over a string of zeros and ones, 6 bits in nature, and then generating to me an output where m is equal to 1. So output will be 1 bit, and that particular bit could be either a 0 or a 1. So this is essentially something like this. These are the 6 bits of an input which will drive and then generates an output which is either a 0 and 1. In this particular case, the OR defines the fact that the output will be equal to a 1. Similarly, for the case of a XOR, which is also identified as a parity gate, wherein you define input string and the output once again could be either a 0 or a 1 depending upon the parity evaluation out over here. So essentially, when you look at the sort of a quantum querying model, you have got this input, and inputs are treated as a series of queries. And then you have the computation. The computation typically will generate the required output, right? So it is a series of queries that come in as an input that drive the computational model. And this series of inputs could be maybe in the form of either iterative applications of the input, or maybe one after the other, the sequential application of the input, and so on and so forth, depending upon the problem requirements. Okay, so we'll now define this algorithm. This algorithm is called the Deutsch algorithm. I think I can take about 10 more minutes, and let me just explain to you what this Deutsch algorithm is all about. The Deutsch algorithm essentially is once again defined as a black box, right? An oracle. So oracle is just nothing but a black box whose functionality is not exposed. We really do not know the functionality. So it is a black box. How it got implemented also we still do not know. But what is essentially known is something like this. We just know the input-output behavior, right? So which also means the fact that if at all I have a mapping, something like 0, 1, this is my alphabet, and n bits of an input, which typically could be any one of the combinations which I can generate out of 0 and 1. And this will generate an output which is either a 0 or a 1. So essentially what do we mean by that? An oracle is this black box which takes an n-bit input string of zeros and ones and generates an output which is a single 0 or a 1. And what is the outcome? Whether it is a 0 or a 1, that all depends upon the function that is implemented in the oracle. For example, if you take n equals to 3, the input could be any one of these occurrences of 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way going up to 1, 1, 1. And it will typically generate an output either a 0 or a 1. So this is an oracle. So having identified what is an oracle, let us now define what is the meaning of this algorithm. Let me put this here. Fine. We will now talk about the Deutsch-Josa algorithm. So the Deutsch-Josa algorithm essentially is a general definition of an algorithm which tells me whether the oracle is balanced or constant. Now, what do you mean by this balanced or constant? Now, remember, oracle is implementing a function, correct? So when I say that my algorithm tries to figure out if the oracle is balanced or not, it figures out whether the function implemented is a balanced function or a constant function. So what do you mean by balanced function? A balanced function typically means that for these combinations of input, for half of them, the output is a 0. For the other half, the output is a 1. Okay? Whereas a constant function is one such function, whereas irrespective of the inputs, the output is always constant, either at a 0 or a constant at a 1. So technically speaking, what I should say is a balanced function is essentially a non-constant function. right? So which means what? Let's say out of 8 combinations, I could have 3 combinations which are 1, 4 combinations could be, let's say 5 combinations could be 0, it's still not balanced, right? So what do you mean by balance function? Balance function essentially means the fact that out of these 8 input combinations, the outputs that are generated 4 times it is 1, 4 times it is 0. So that is essentially what we mean by the balanced or a non-balanced function. And the Deutsch-Joshua algorithm, if it is maybe brought down to maybe a single bits, then we get this as a Deutsch algorithm. So it is essentially a reduced Deutsch-Joshua algorithm. Okay, so let me move to the next slide to just illustrate this particular concept very quickly. Here is a function, and this particular function is something like this. You give any input, then you perform an ANDing with 0. So this ANDing is represented by a dot, and this is a classical AND operation. And this classical AND operation gives you an output equals to 0 always. So this is a classic example of a constant function where the output is 0. It's a constant 0 function. Similarly, if at all you have, let us say, a classical OR operation with a 1, irrespective of whatever is the input, the output will always be equal to a 1. So essentially, we also have that. But whereas if you have an XOR, then obviously you have maybe a balanced type of gate. For some, for half of the inputs, it could be 0. For the other half, it could be a 1, and so on and so forth. So this is a classic example of a constant function. So if I take n equals to 3, I'll have all these combinations. So this function is x2 dot x1 dot x0 dot 0. So this is my implementation, and this implementation yields always an eternal 0. So this is a classic example of a constant oracle output giving me equal to 0. This is similarly yet another example. And here I am talking in terms of the function over 3 bits, x2, x1, and x0, and the definition is x2 exclusive or x1 exclusive or with x0. So this is my classical exclusive OR operation. And if at all I just put them out over here, so this is my function outcome. You will see the fact that for about 4 input combinations, the output is a 0. For the remaining 4 input combinations, the output is a 1, because of which this is a classic example of a balanced function or a balanced oracle. Okay. A third example. We are typically taking this particular function. So what is this function? I'm now defining a function called UF operating over 2 qubits, x and y. And my function definition is as follows. The output of this will be once again 2 qubits, where the first qubit is the same, the most significant bit x is the same, unchanged. And the second qubit is now an operation that is carried out as follows. So the second qubit is defined by y as it is, exclusive or with the function operating on the first qubit. So the second qubit is defined by the second qubit exclusive or with the function operating on the first qubit. So that is the way I have defined this sort of a function. And what now we can do is something like this. Let us say my function f of x is a constant function. And I will also now say the fact that it is a constant 0 function, which means what? F of x is equal to 0. And if at all I assume that my f of x is equal to 0, and if at all I plug this in out over here, you will notice the fact that the input 0, 0 will generate an output 0, 0. 0, 1 will generate 0, 1. 1, 0 will generate 1, 0. And 1, 1 will generate 1, 1. So which also means the fact that there is no change in the input. So the inputs are passed on as it is at the output. So I can now say the fact that I have an identity operation that can now be representing my oracle. So I said the oracle is represented by the identity operation. So let me take yet another example here. So let me say that once again f of x is a constant function, and that always gives a 1. So which means the fact that f of x is equal to 1. And then once again putting up in the same manner like I showed earlier on, you will now notice the fact that 0, 0 gets transformed to 0, 1, 0, 1 gets transformed to 0, 0, 1, 0 gets transformed to 1, 1, and 1, 1 transforms to 1 0. And because of this, I can now say the fact that this is an implementation of a SEX gate. I think I made a small mistake somewhere here. The 0 0 should be, these two should be flipped. Okay. So, but the fact is the oracle is implemented by a CX gate, right? Controlled NOT gate. And similarly, what I can also do is something like this, taking the same function, and if at all I say my f of x is a balanced function. So what is a balanced function? For some inputs, it will have to be 0. For other set of alternate inputs should be a 1. So you have to have equal representation for the outputs to be both 0 and 1. So here is a small example. I define a function which says if the function is operating on 0, I get an output 0. If the function operates on a 1, I get the output equal to 1. So this is a balanced representation. And if I operate on that, they will have an oracle implemented by this. It's once again a C0 gate, but the target line and the controlling line are flipped. Okay. So this is how I can identify what really goes into the, let us say, my oracle. I'm not getting into the details, but you can derive this also mathematically. And that goes into designing your oracle. What really goes into your oracle, you can actually evaluate, and that can be implemented. So in the context of my Deutsch algorithm, this is my complete quantum circuit. My quantum circuit is something like this. I'll just show this picture and then flip over to a small 5-minute demo, and then we can wind up the session. So here my Deutsch algorithm typically takes the inputs which is in the form of plus minus, right? And what it does is it keeps the MSB as it is, right? And flips the bit to -1 if it is balanced. Keeps it as it is if it is a constant. So which means what? My Deutsch algorithm can be typically used to determine if the oracle is a constant oracle or if it's a balanced oracle, right? So to implement this, what we essentially need is something like this. We take the inputs, and maybe if at all I would like to generate a 1, so I just use the X gate to complement it. So here now my state will be get 0 1, and then I give it to a series of Hadamard gates. So this is also called as a H2 implementation, 2 Hadamard gates operating on both these 2 qubits operating at the same time, and this will just give me basically a representation of plus minus. So this 0 will be represented with plus, and 1 will be represented with a minus. We now know about the working of Hadamard gate, and this is what is given to my oracle implementation. And what is my oracle implementation? This is a function, the same function which I defined earlier on. And once the output is generated, I now need to measure this, right? And remember, this output is typically in the plus minus basis vectors, the basis space. So I need to rotate it back to the 0 1 basis, and that is typically done by applying yet another Hadamard here before I actually measure it. And when I measure it, remember, I'm just only measuring the most significant bit, the MSB out over here. The MSB will tell me if it is not changed, if it is still a 0, it is a constant gate. If it is a 1, it is a balanced gate. So that is how my Deutsch algorithm works. And if at all you look at the implementation, this is how the implementation looks like on the IBM Q. Right? You can just drag drop these things and just implement it, and then if you run it out over here, you will get this implementation indicating the fact that this is a classic example. I'm using I's. Remember, what is that I? The identity, and that identity will be representing a constant 0 implementation. So here the function f of x will be equal to 0, and because of that, the most significant bit to observe will be equal to a 0. So the simulation state gives me 0, and if at all I just run it on a real computer, I will get this also a 0, but the probability out over will be something like 0.997, something like that. There would be a small component out over here for the state 1 0, and that is more or less reasonably insignificant as well. Okay, so this is similarly for a constant 1. So for a constant one, I'm now going to represent that oracle by this C0 gate. And the moment I represent it with a C0 gate, I will see the fact that once again the outcome will be 0, 0, indicating the fact that the most significant bit is a 0. So it is a constant gate. And finally, this is a picture for representing or implementing a, let us say, a balanced oracle. And the balanced oracle can be represented by this. It's once again a C0 gate, but we flip the roles and the responsibilities of the control and the target bits. And the moment I have done that, you will see the fact that this is a balanced representation. So you'll see the fact that the most significant bit is a 1 here. So the state is a 1, 0. Most significant bit is needed to be observed, and that state observed will tell you the fact that it is equal to a 1, indicating that this is a balanced system. Remember, we talk about f of 0 is equal to 1 and f of 1 is equal to 0. So that is my function implementation. Okay, I think I've gone beyond the scheduled time, and next time I will either pitch in or I'll have Prakash to just show you a quick demo on IBM Qiskit. Okay, so if there are any questions, kindly. Yeah. Fine. Okay, I think I have another 10 more minutes. Thanks, Prakash. So I will quickly run through the demo. Okay. So this is where we are. How do I knock this off? So irritating for me. Okay, I'll put it somewhere here. Okay, so I'll quickly go through the code and then I'll just run through them rather than sitting down and creating them. So I've got these programs which are there already with me, written down. Come on. Yeah, my workspace needs to be refreshed. So here I'm talking about one project, which is the Deutsch 0 constant implementation. So remember, for constant implementation, this is going to be a 1, 1 here, right? So I've got the input. I just have put up an identity, and then I'm going to use the Hadamard gates out over here, and this will now put them into superposition. I'll give it to this. This is my oracle. So this is my stage 1, this is my stage 2, and this is my stage 3. When I once again use the Hadamard gate, and then I have a measure. And directly, if you just observe, the output is coming down to 0, 0. What I will do is I just run the code one more time with what we call as inspection. Inspection allows you to sort of move across the timeline of your circuit. So it allows me to go stage by stage, step by step. Okay, so the moment I am now into the inspection mode, so this is what I actually see. Don't worry about this. This position is shifted out, drifted out, because by default, this will try to squish all the inputs. Okay, so what I'll do is, as the first step, I'll just click on this. See, this is the trigger to execute layer by layer. So I just execute the first layer. It's something like the first point of time. So here I have my inputs, which are coming out there, and I go to the second stage. Okay, just hold on. The system is taking a bit of time. Yeah. So I have put the entire thing into superposition, both the inputs. So I have got equal probabilities of 0.25 all throughout. And then I'm going to the third stage, wherein my oracle actually is now executing. And because it is identity, you don't see any outcomes here. Now notice the fact that my Q sphere shows the participation of all the 4 states across north, south, east, west directions of my globe. And then I click on this, move to the subsequent stage. And now here I have put up on the Hadamard, wherein I just move the observation post down from my plus minus to 0, 1. Because measurements are done in my 0, 1 space. right? So the moment I have put up that Hadamard here, now notice the fact that I will get typically equal probability happening out there. And now let me take a measurement. And the moment I take a measurement, okay, the system collapsed and then it gives me a state of 0, 0 with a probability of 100. And in this, my interest is this most significant bit 0, and the most significant bit 0 tells me the fact that this is essentially nothing but a constant 0 type of a behavior. So this is a constant 0. Similarly, let me look at Deutsch constant 1, right? And right, this is my circuit for my constant 1. If you remember, once again, these are my inputs. I've got Hadamard to create the superposition, and my oracle is my conditional NOT, and then at the outcome I have got Hadamard gate with a measurement. Pretty very simple. So let me once again run this in an inspection mode. Okay, so I will first execute. Fine. So this is my input. So input will be 0, 1, and subsequent to that I will push them to the H2 state, the Hadamard gates, and now I'll have equal probability of all the 4 states, 0.25. And now I will have the oracle trigger on this, right? So the oracle works on this and it performs its operations. And notice the fact that it will just create the outcomes depending upon the possible probabilistic states of the outcomes of H gate. And I will now move further and then make this available to another Hadamard gate, which will transform these states from the so-called two-dimensional Hadamard space or the H4 space, I should say, or sorry, C4 space down to the C2 space, right, from the plus minus to my 0, 1s. And having said that, I have once again equal probability of 0, 0. And if I just move this further at the point of measurement, I will see the outcome to be equal to 0, 0, indicating the fact that this is also a constant input. Remember, this is my constant input, right? So rather it is a constant oracle, but this time it's a constant 1 oracle. So either it is a constant 0 oracle or a constant 1 oracle, it is immaterial. The most significant bit always will be equal to a 0. So let me go across and then try to implement and show you the implementation for the balanced. Okay. Now for the balanced, the circuit representation is quite the same. So now you have to have a reversal of this C0 gate. I told you about that. And once again, what I need to get is an output where the output will have to be equal to 1. And that bit has to be equal to 1 to indicate the fact that it is balanced. So I will quickly simulate this step by step. So the starting layer, I started with a 0, 1, then put them into superposition. So I get 0, 0, 0, 1, 1, 0, 1, 1, equal probability of 0.25. And then I will subject this as an input to my oracle and subsequently grab the output, drive it through the Hadamard gate. So this once again will be this state representations. And the moment I measure them, the system will collapse and I get 1, 0 as the outcome. And in this 1, 0, all you need to observe is the most significant bit equal to 1, indicating the fact that this system is a balanced system, right? It's not a constant system. So remember, we had the function implemented as f0 is equal to 1, f1 is equal to 0. So this is an example of a constant system. Okay. So that more or less completes my session for the day. And in case you have any queries, you can either pump it here, or you can probably put it into the chat window, or you can also send it across. We will be in a position to answer that during the next session. Okay.
Hey, Gokal.
Hello.
I just wanted to say that I really like the fact that you went through the Deutsch algorithm and showed some quantum circuits that implement the oracle. That's usually something in the literature when you see it in whatever dissertation you're looking at, they just say it's an oracle. So it's quite an exercise to go through and actually try to come up with the circuits that implement the oracle. So it's pretty nice that you had some samples where the oracle just isn't a black box; it's actually quantum circuits.
You're right.
One other thing I wanted to mention is, and I think this is kind of a theme with this course. You have the order of the qubits listed as Q0 is least significant and Qn is most significant, which is consistent with most platforms. But I notice you invert a lot of these algorithms. Generally, when I see the Deutsch algorithm portrayed, the input registers are always the least significant, and the ancilla
Correct.
qubit is always the most significant. And you seem to have that upside down. For your presentation, it doesn't make any difference.
Correct.
The algorithm doesn't care.
Yeah, thanks, Ram, for bringing this up. I was just
But
actually going through the standard notations from the IBM Qiskit, and there is
yeah,
always a confusion. The moment you pick up yet another textbook, they just flip this order, the most significant and the least significant bit order. But what you said is perfectly right. I could have just flipped up the ancillary and inputs, and still I could
yeah.
have gotten the same result. Thank you
So
so much.
one benefit of making your ancillas the MSBs is now you can state your input register as an integer.
Right.
And if the ancilla is first, then it's a little confusing to state the input register as an integer. In the case of the circuits that you demonstrated, you only had one input bit. But if you had two or three input bits, then
Very true.
if it's like qubit 0 through qubit 2 for 3 bits, then you can state it as an integer. Whereas
Yeah.
if they're the high order bits, it gets a little confusing.
Yeah, you're right.
Um, One other comment at the beginning, you mentioned the oracle is a black box, which is part of the algorithm. Um, One important thing to note about it, it is a black box, but the basis of the algorithm is that you are also given a promise, right? The
Right.
promise is the oracle is balanced or it's constant. So
Correct.
if you do some math, like on a single bit input, you run the Deutsch with a single qubit, people maybe, you can calculate how many possible functions there are for that oracle.
Right.
And also based on the fact you only have a 1-bit output, you can calculate it and it'll come up to 4
Four. Yeah, we
possible
call them as
functions.
function A, function B, function C, and
Yeah.
function D. Yeah.
So in the case of 1 qubit, they're all of them are viable. In the case of let's say 3 qubits, it's 2 to the size of the state vector, so it's actually 256 possible
Right.
functions.
Correct. Correct.
Not all of them are viable because not all of them will meet the promise, right? So that's something that it's good to understand when you're doing this. It's again, you are given a promise. You don't know anything about it, but you are given the promise that for this algorithm is balanced or constant. It's not some algorithm that is somewhere in the middle, and
Right.
so that's an important bit.
Yeah.
Um,
Appreciated. This is, I think, very important input. Very frankly speaking, I just, barged in for today's session. I was not too very clear as to
yeah,
how much was done prior to this session. So I assumed some inputs, and then I've taken over from there.
yeah.
Yeah.
But
I
once
would
again,
say,
I really like how you showed circuits that implement these oracles, at least for 1 bit. I would encourage people to try to jump up to 2 bits as input. So you have 2 input bits and 1 ancilla bit. Try to figure out what pick your function and then try to figure out what the quantum gates would be to implement that oracle for a 2-bit input. It's a great exercise.
Right. You're right.
Ron, Prakash here.
Hi,
Thank
Prakash.
you for the feedback. See, one thing you remember, we had the discussion in this earlier also on the qubit versus mixed states. So pure states is easy to converge, but when you have a mixed state, then you don't know how many number of mixed states are there, and that is where the challenge comes. And even if I go by POVM versus PVM, what they call, I sent you a link, I think.
Yeah, I went through that a little while ago. Yeah.
So the mixed states is a, see, when you have a surrounding, you don't know what's surrounding you, and
Right.
that's where the complexity arises in mixed states, and they are maximally entangled or even less than that. Then how do you compare? Like they say about POVM versus PVM, that is, when we do probabilistic projected measurements of probability versus the POVM, what they call, which is the quantum mechanics phenomena. There I find that convergence is very harder. And so when you talk about these, what you call the universal computation and universal gates and unitary, reversible, and trying to get to the balance constant, every time we see that it is always going to be N to M. And when you say N to M, N is your input string, whatever you want to do, whatever algorithm you apply, you have to converge to finally only one. There is one output if you want single output. If you want multiple outputs, then you'll have to put so many equivalent ancillaries, right? So N and M, if M is equal to N plus 5, then you have to have 5 more qubits for the output, because inputs and outputs have to be separated out.
Yeah, especially for studies on things like the Deutsch algorithm, or any of the other classic I refer to as toy algorithms. They're toy algorithms, but they demonstrate a feature of quantum. You'll drive yourself nuts if you try to jump in with mixed states.
Correct.
Start your understanding with the 1 and 0 states.
Even simple like Simons, Grovers, and even what you call Shores, even to that extent we can do. But beyond that, if you get into really chemical genetics and proteomics and all that, then it's very complex. Very complex. Without mixed states, you can't do it also. It's not like, that means the computation level will be very high.
Yeah, well, that actually brings up another topic, and I responded to that email, and I went through that document that you sent me the link on, and I'm like, I'm starting to doubt whether I understand certain things about eigenstates and eigenphases, which are the complement of eigenvectors and eigenvalues in linear algebra. It seemed to me that article was stating things a little.
The reason for those eigenvectors, eigenvalues are because you cannot touch, you cannot measure. If you measure, you collapse. So you have to go to the properties to evaluate, and the properties could be position, moment, velocity, acceleration, whatever. So anything associated property only we can measure to conclude this is what it is, without destroying the qubit themselves. And that is the challenge. And because of that, the question you raised, how do we bring those levels, is the question. Can you repeat again your question? I was trying to answer it and then I lost track.
Again, and what I suggested in the email was that we try to have a session that really gets the concept of eigenstates and eigenphases nailed down, because I see that sometimes I'm reading something and I think what they say eigenstate, which is interchangeable with eigenvector, but they might be meaning the eigenvalue or the eigenphase. Actually, in that article, I think it said the eigenstates for the Pauli operators is plus and minus 1. I think they meant eigenvalues. I'm not sure about that.
Gokhale has also dealt with it. We
Yeah.
concluded that eigenvector has to, whatever eigenvalue you get at the end of it, it should be measurable. It should be a it should be a real number, and most likely it is integer and plus or minus 1. So whatever we do at the end of it, when it collapses, it has to result in plus or minus 1, or maybe something different also. It is not necessarily plus minus 1. There are eigenvalues which can be √3/2 or some such combinations, which are 0.707 times. But then it should be measurable. Without measurability, and measurability being plus minus 1 is easier than anything else. Therefore, you try to collapse it to that. Now, corresponding to that, what your matrix turns out or the vector turns out, which is Hilbert space vector and matrix, has to make sure the trace of it is equal. When you do a what you call trace of the diagonal matrix divided by the normalization, it should be plus minus 1. And a trace measure.
I think we can come up with a better definition of what an eigenstate is in quantum land than defining in terms of the matrix. And what you started out, you're talking about mixed states. Well, a whole bunch of these algorithms use the VQE, because eigenstate, or sometimes you don't know. Sometimes the challenge is you've got this state, which is like a Hermitian or a operator. You get this big H matrix because it's what you're trying to solve, and what you're trying to find are the eigenstates for that thing, and you don't know what they are. So that's why I think it's really important to understand for a simple state like just 1 and 0. What are the eigenstates for each one of the Pauli operators, for example? And eigenstates, it's not the eigenphase or the eigenvalue. It's what state, and what are the definitions that make those make them eigenstates for a given operator. And again, when you start understanding, then it starts to become clear how these VQEs, for example, work and why they're important, and how they get things like in chemistry and hopefully in computational bioinformatics to make more sense. And now that I said that, I also have to thank you for that article you sent me on bioinformatics. Unfortunately, there wasn't anything in there about quantum, but it was fascinating.
Yeah, there is nothing about quantum. But what I meant was that's the one where applicability is very, very high.
Yeah. No, it's a great reference for me. I kept searching through it for quantum algorithms.
No, there is no quantum.
I'm not too sure about that article, but that reminds me of some sort of a gap search, which I used to do almost about 25 years back when I was toying over this bioinformatics arena. Like even you talk about extremely large strings, maybe a million strings, and then you try to find out the substrings which are there, and then try to find out what exactly is the gaps that you can find out, extract the gaps, and then if at all you can just punch them together, you might probably get your original string. So those sort of things in the context of protein interactions, they come into
sounds like you have a great understanding of the complexity of those tasks.
Yeah, I have done that, I've almost about 25 years back that time, and then we were struggling writing codes in Java. And yeah, we had bio Java that time, right?
And all this, keep in mind, everybody, is that Qiskit's been out for 6 years. So there's people with PhDs, there's people with postdocs that have figured this stuff out. Like it's part of their training. Now, if you think long term, because some of the discussion you're talking about is going towards machine learning with pure states and all the entails with that, is that you want to think like, you know, in the future, how can you succeed? Because this is probably at least my 12th or, you know, at least over 10 discussion where it's just very, very basic, but the industry has a lot of experts in it. I mean, there's some on the forums, there's some on Qiskit, and there's some on Penny Lane, but like you want to think in terms of like software, like the actual the languages. So like if there's a brand new announcement, like, you know, Penny Lane just supported multi-node support for multi-GPUs, and now there's like national labs working on that. Like, how can you, like, because everybody's looking for something. People either want jobs, they want to further their company, but how can you make it in the quantum world? Because a lot of this stuff, it's just standard. If you go to apply somewhere, everything pretty much in this discussion is standard knowledge. You have to know. So they're going to be looking for some other things. So the basis is good, but it has to be moving towards like, you know, advanced workflows for QML. It has to be going in specific areas because nobody's going to hire anybody if it's just the principles, which is what this discussion was.
Sure. Kevin, I appreciate that. The issue has been the industry, more of the government funding is what is driving it right now. Like I am here at the conference where I met Jensen Huang, our what you call the NVIDIA guy. See, they have Q quantum, but somebody has to apply this, right? Most of the people are running away right now, not even clear about the quantum algorithms. Then
yeah, but it's also possible to get stuck with it too. Because say, for instance, with Penny Lane, there's a whole section with this of how to do, and I just presented on this with MPIs and, you know, the conditions in order to do that. But I don't get that sense as far as like, you know, there's this huge movement towards, you know, memorizing these libraries and implementing the code and, you know, working into workflows. Like, you know, that's just what it is. Because like if there's, you know, a boss that saw this presentation, says, yeah, he or she says, yeah, you know, these are just the requirements, but you really have to get into the languages, you know, Qiskit, Penny Lane, Circ, whatever you want to use. So, you know, it's just a trend. And like I said, Qiskit's been out for 6 years. Penny Lane's been 5. And when I go to other discussions too, it's not just this one. The wheels are stuck in the basic, you know, notation.
True. Basic notation
yeah,
are now getting better.
Yeah, in 2 or 3 years, you know, an expert in theoretical, you know, quantum physics and, you know, the basics like this, there's already people that have like advanced degrees in this, right? So that's what I'm saying is you need to, you know, make that push towards, you know, the languages. So after a few iterations, like release notes, they keep releasing these, then all of a sudden you might be in the front lead to make the next application. So it's very easy because everybody goes through this phase. Like, yes, you have to know circuits and you have to know composer, you have to know lab. And if you're doing, you know, Penny Lane and Circ and comparing all these 3 or 4, but that's ultimately where the applications are, is the notation of writing computer programs. It's not the, you know, the physics. Now, there are people out there that are awesome with quantum physics, but like I said, to get to those points, it's going to take, you know, PhDs and postdocs and many postdocs to the point where you have that theoretical, you know, they understood eigenvalues and everything maybe in the first couple of semesters. So that's what I'm saying with languages is they, you know, it's free game. Like it's really, really hard, right? Because you're responsible for all this stuff, but you don't need PhDs and you don't need postdocs to do that.
Yeah, so domain-specific language drive it. So the industry-specific we have to be. So if you are healthcare-specific, then you must focus on that. Then only you can translate that domain-specific advantage over the use of whatever quantum regular stuff.
Well, it's just, I mean, it's just talk at some degree because, you know, until people actually like become experts in a certain area. Say if you want to be an expert in Qiskit nature, right? Or you want to be an expert in Qiskit dynamics. That's where it's at. I mean, it's the type of stuff that's talked about here. I mean, it's a lot of basic stuff, but also I get that sense where you just want to be stuck in figuring out quantum as opposed to just applying things, right? You're never going to get to 100% with all the basics, you know?
Yeah. So it means that the tool experts have to be there, whether it's a penny lane or whether it's a Quiskit.
Yeah, but we already have
And
them.
then having those people with the domain experts who can bring the domain knowledge to apply to it.
Yeah,
Then
but we already
otherwise
have, like, there's a paper that was written in the 90s. It's the big table of quantum artificial intelligence. And a lot of it, we didn't have the simulators to run and, you know, the CCCQ, QCQQ kind of stuff. And they didn't have hardware to run. And, but the idea was there. Like to make a quantum simulator is very easy. You just have to understand quantum mechanics, and then you're off and running in QML. But I don't get that sense here that that's the push, right? Is basically to design code and, you know, the next applications. Because I mean, what you're talking about, you could work your way up to be an expert in your specific thing, and everybody refers to you because you know everything about quantum. But at the end of the day, I think you'll find that it's more, you know, you have the application. You know, you've been working on your model for a while, and, you know, it's something tangible, like something practical, because there's value in these things, right? To be an expert and then go into practical stuff. But I think that's what you'll find is you have to pick an area that interests you, if it's finance or transportation or medical, and then start applying it with code. Because many people, you know, it's one of those things you can memorize a million facts with these types of things. And yes, you have to know the basics, but then to take it to the next steps with, is this ready for industry? Like the workflow. I'm just saying, if you don't adopt something like that, is you will not have a very good chance of making it in quantum, because like people go to school for this, you know, like many, many years. And it's hard to learn the basics and then try to outdo them and these types of things without getting into like Qiskit and penny lane and your own applications.
Yeah. So
if I may tell something, I think the basic objective of this 6-session series was to maybe, you know, tell our participants about what exactly is quantum all about, and trying to demystify the core concepts behind that, so that at least they don't run away from that. So
these frameworks have been out for many years, and that's what I'm saying. It's not just this one; it's other ones too, where it's basically that push to go advance, right? Because this discussion could have been given 5 years ago, right?
Yeah, you're right.
Yeah, because composers changed a little bit, but it could have been given 5 years ago.
Right.
True. So we will take up advanced courses as we move, but this year I think we will be limiting to this to get a bunch of people who are interested. And then if some of them can get into jobs in that industrial area specific, that would be a great achievement, because it's not like we alone can drive it. We are also looking at what governments can do, where we can. So tomorrow, obviously I'm going to the the Seattle to attend the Quantum Week, IEEE Quantum Week. Ron, you're aware, and Kevin, you're aware. We are trying to find people there, and hopefully we can gather some people and see what, because all these national laboratories and all, they are definitely doing great, but they are still not there as we would like the industry to accelerate. And that's where the challenge is. How do you get the subject matter experts to apply it and fund it through the Silicon Valley? Here we have like Sequoia and other capital who can really.
If it helps, it's less about, because I've gone through these stages too, what you know in quantum, and it's more about what you did and what you're doing. You know, like it's like, yes, it's hard to read books and it's hard to, you know, get certificates and all these types of things, but it's like, you know, if you could show them, because when you go to these conferences, the people presenting the posters, they have an abstract, and this is all the computer work they did. So I think it's possible for anybody to go in that direction. It's just, like I said, it's just like after the I don't know, past couple of months for me and getting into stuff, advanced with quantum is just, to keep coming to these, and they're just like basic. And yes, if you go more advanced, you will lose some people. But I think what you'll find too is a lot of people that just come from the basic, it's just too over their head for them, right?
Mhm.
So it's balance, right?
Mhm. Yeah, so this is where we are also looking at the hardware side. The software is one part, the hardware is there anything, should we have to use a super cool? Why can't we do with, example, let's say a diamond with a NV?
Yeah,
Can
I mean,
we
it's just it's the phase that
look
you
up?
go through. It's just very broad. I know it's hard, right? There's many things out there in quantum, but once you get to that stage and like, oh, I just want to work on, the specific thing in Qiskit nature, and it's just building, and it'll kind of narrow down. But yeah, I mean, not especially small organizations and small groups of people, they can never, it's really hard to do both hardware and software. It's hard
Correct.
enough just to do hardware because it takes so much capital.
Correct. Absolutely. That's why the government's funding is important, and the national NIST has really started looking at it, and CHIPS Act is there. So how to tap in also is a big art. We'll have to figure out ways to tap into these funds so that we
Yeah,
can create the quantum jobs.
I just did 100 discussions, and I'll tell you this: that's what I found is my only chances with software, like for small guys, unless you have millions of dollars or the backing of some other national labs, those types of things.
Mhm.
And you can get into software relatively easy. And I mean, you're working on it every day, writing code, and it's not just algorithms; it's like the whole model, that type of
Correct.
stuff. So that just seems, unless you have a lot of money to get into hardware, but you really have to pick something. And that's the other
Correct.
thing. It's just like you did the research, like this industry makes, this industry is valued. There's 3, valuations post $1 billion. You make up your mind that that's what you're going to do. And, getting to that point is hard. And yes, I've gone through these stages where it seemed like everything in quantum is awesome, but you're limited in the number of hours you can work. And you'll find once you get into a specific area that area gets deep, much deeper on its own, like QML or, Qiskit nature, those types of things.
Sure.
But yeah, you guys are on your journey. So, it's nothing to be, you've researched a lot, but just keep in the back of your mind is just that, the stuff, the fundamentals and, just how to run circuits and composer and lab and these types of things is that eventually you'll have to get to the point if you want a job in quantum, or if you want to start your own company where you're doing work that very few people want to do because it's too hard or it's novel. So yeah, I would say, yeah, just, keep on the path, but you'll have to settle, like focus on a specific area. You can't do everything in quantum.
Correct. You're absolutely right, Kevin. Dot on that. That's why important thing is to get to learn the basics, then move on to the special area or specific. It could be tools area, it could be application area, it could be algorithm.
Yeah, and
area,
it'd be cool to see what you learn. I don't plan on heading up to the conference, but it'd be cool to see what you learn. Somebody else asked if I was going. And then in specific, is there a certain type of area you want to get into? And that's like a gold mine, talking to these people who have done the research in the labs, and they can kind of steer you in a certain direction, even within that narrow spot that you're looking at.
Correct. Great. Gokhale,
Yeah,
shall
thanks.
we
I
close?
think we will close the session. Thank you very much. Thank you, Ron, for your inputs, and thank you, Kevin, also for your wonderful inputs. Frankly speaking, I'm a newbie into this entire area, and I think I've been with quantum, I think for the last maybe 2 years, with a break. There was a small break also in my exposure to quantum, and of late I just got reasonably entangled into this domain, and then I'm spending a few hours every day apart from my other obligations, and I'm sure I'm going to now pump in a little more number of hours and then try to pick up some domain and work towards that particular objectives.
Yeah, and best of success to everybody.
Yeah. Yeah, I need
Thanks,
to do
thanks
that.
everyone. And Gokhale,
Thanks.
I think you can close the session with
Yeah, I'll
stopping
close
the
it.
conference. Okay. So
Yeah,
that
I'll do
will-
that. Thank you so much. Good night and
Thanks
have a
everyone.
nice day, all of you. Yeah.
You too. Ron, thanks.
Bye-bye.
Take care. Kevin, bye. Gokhale, bye.
Thanks, guys.